Okay, so section 3.3, understanding graphs, analyzing graphs, looking at rates of change. We're going to continue on. And I actually, believe it or not, I just thought of this like 2 hours ago. And I said, hey, this might be a good way to talk about rates of change and graphs in math class today. So I went out to my car. Never done this before, so you guys bear with me here. I went out to my car, and my car it's got all the digital whatever, miles per gallon, and time, and trip odometer, and distance to empty. You guys know what I'm talking about. All the kind of electronic stuff that's on your dashboard, depending on how old your car is. And so this is like my trip odometer. And every time you reset it, it goes back to 0, right? Well, obviously, I haven't reset it in a while. So, do you guys know what this means? Since I reset my trip odometer, I have traveled 1,619.9 miles. And the engine has been running for how long during those 1,600 miles? 62 hours and 56 minutes. 62 hours, and so almost 63 hours. So, think about this. As my car, the last 63 hours that the engine was on, the car has traveled 1,619.9 miles. Does that make sense? So here's my question. If this is miles and this is hour, I want to talk about rate of change. And when we drive, we typically label it, unless you're from Canada, we label it miles per hour. If you're Canadian and you like kilometers, I'm sorry. We're going with miles today. Okay? Miles per hour. So my question is, since the last time I reset the trip odometer, what is my average speed? I'll give you a minute to think about it. Use a calculator if you want. What is my average speed in miles per hour since the last time I reset my trip odometer? Now, is 62 hours and 56 minutes the same as saying 62.56 hours? No. You got to convert that minutes. 56 out of 60. That's the same as saying like 62 and 56 sixtieths if you think of it as a mixed number, right? So what is that in a decimal? Do you guys know what this is in decimal form?
93.
Yeah, 0.93 repeating. So it's not 62.56, it's 62.9333. It doesn't make a huge difference, but that'll change your calculation just a little bit, right? Anybody got an answer? 25.7. Anybody else get that? This isn't real heavy math. It's total number of miles divided by total number of hours, right? So what I'd like you to do, so we know that our answer is supposed to be 25.7 roughly, 25.74 or something like that, right? That is my average speed, and that is in miles per hour. Let's keep that in mind as we move forward here. Now, let me show you another picture. I can actually toggle my little whatchamacallit on my car, and sure enough, see the average miles per hour? That was on the next screen on my car when I hit the next button. 25.7. Do you see how my car calculated it? Calculated it the same way you guys just calculated it, right? 25.7. And on a side note, I'm getting terrible gas mileage. Okay. So here's what I'd like you to do. I would like you to open up your GeoGebra graph. And I want you to set your axes. I'm going to make my font size bigger so you guys can see it here. I want you to set up your graph so that we're only looking at the first quadrant, just the upper right. I need you to scrunch your x-axis all the way over so we can get to, 62.9 hours? So scrunch it over so you can see 62, 63, 64. See how I did that on the x-axis? And how far do I have to scrunch the y-axis down? Because my y-axis is going to be miles, right? So I got to get to like 1619.9 or 1620, something like that. So scrunch it down until you get past 1600. You should have a graph window that looks something like mine. Everybody there? I want everybody to have a similar picture on their screen. And then we're going to plot 2 points. Right when I pushed reset on the trip odometer, we're going to call that time 0. Okay? And when you push reset on your trip odometer at time 0, how many miles are now on your trip odometer? Anybody ever reset the trip odometer on their car? 0 miles, right? Do you guys agree that at time 0, I would have gone 0 miles? So plot the point 0, 0. That's our origin point. 0, 0. What's the other point I'm going to plot? Let's plot the point as it was this morning when I went out and took that picture in my car. How many hours? 62.93, comma, how many miles? 1,619.9, I think is what it was, right? Did I do the number right? 1,619.9. So there. I now have 2 points. I have the beginning point when I first pushed reset. And I have the ending point as of my car sitting in the parking lot right now. And then what I'd like you to do is I'd like you to connect those 2 points with a line. And then when you have your line, I'd like you to right click on it, we've done this before, and change it into y equals mx plus b form. And you should get the same equation that I got. Y equals 25.74x plus b, but the b is 0. That's why there's no y-intercept, right? Plus 0. 25.74. That is the what of my line? Somebody said slope. That's the slope of the line. Did you guys know that it was going to be 25.74? You should have, because what did you just calculate? On average, my car is going 25.74 miles per hour. Okay, true or false? If you see Jamie driving down the road, there's a pretty good chance that he's going to be going 25.74 miles per hour because that's his average speed. So normally Jamie drives 25.74 miles per hour. True or false? Do I spend most of my time driving 25.74 miles per hour? No, I don't. Why not? Somebody explain this to me.
Because half the time you're going like you're on interstate, you're going 75, and half the time if you're like driving through town, you're probably driving slower, or like cars just running.
Correct. Very good. Sometimes I go to Fargo a lot. How fast do I drive on the interstate? 79 miles per hour, sometimes 80. Okay? I'm afraid to go 81. I think I might get a ticket, but I'm comfortable at 80. Okay? So a lot of times my car is going 79 miles per hour. A lot. But is it also going 0 miles per hour sometimes? Yes. When would a car be going 0 miles per hour? Right when you start it, before you even put it in gear. At a stoplight. When I take out my remote and I push start and warm up my car before I leave the office. The engine's running, but the car isn't moving. Do you see how sometimes it'll be going 0, sometimes it'll be going 80, and sometimes it'll be going some number in between? You guys cool with that? So here's what I'd like you to do. We know that over the last 63 hours, this is not a true representation of my speed. It's the average of my speed, correct? What I'd like you to do, this will be kind of fun. If you have a Mac, you're going to have to use your mouse. If you have a PC, you can use your finger because we are better than Mac people and we have a touch screen, right? Okay, so what I'd like you to do, everybody got a graph like mine? Underneath the pointer tool, grab the pen. You guys see the pen? Okay, what I'd like you to do with the pen is I would like you to draw what you think, everybody's going to be different, what you think my actual speed looks like. We know it's not a straight line, right? Do you guys agree it's going to be some kind of squiggle? But before we do it, let's talk about a few things. What 2 points do we know have to be on your squiggly line? It has to start where? It has to start at 0, 0, and it has to finish at point B, this 62.93 point, right? So you're going to connect point A and B with something that is not a straight line, okay? But it's still going to start at A and it's still going to end at B. Couple other things. Can the graph ever go down? What do you guys think? Right. Negative speed would be if I was driving in reverse. And I'm pretty sure even if I put my car in reverse, do you think the odometer goes backwards? They do on really, really old cars. People used to do that when they, like if you had a car that had 80,000 miles on it and you were trying to sell it, and you'd be like, boy, 80,000, that's a lot of miles. I wish it only had 30,000. And then you prop up the wheels, you put it in reverse, and you let it run, and the odometer goes backwards, and then it's called odometer fraud. You guys are probably too young to remember that because cars now don't have the little dials. Does anybody have a car that has a little dial? Got an old one? Now that's all digital, right? I bet if you put it in reverse, does your odometer go backwards? I don't think it does. You have to have a really old car to get it to do that. So you're right, Katie. My odometer never goes backwards. So one rule is that it always has to have a positive slope. So if you're going to draw this with your finger always has to be moving up as you get to point B. Everybody ready to try it? Go ahead and draw yourself a graph. If you have a Mac, you're going to have to use your mouse. I'm going to use my finger. I'm going to see what I can do here. So I would say mine is okay. Yours doesn't have to look like mine by any means. The only criteria is you have to connect point A and B, and you can never go down. That's the only criteria. Okay, I'm going to come around and look at a few of your graphs and see what they look like. Somebody flag me down if you think you have a good one. If you connected point A and B and you never went down.
Press the undo button right up there.
I think yours goes down. I can see a couple spots where yours goes down. It can't go down. You, like right here, from here to here, you're going down. You can't go down. Does mine go down anywhere? Man. It almost looks like it goes down a little bit right here. I tried to make it flat, but does it look like it's down a little bit there? And maybe just a hair right there, it's down? I tried to make it flat. Who said that? Okay, very good. Does yours ever go down? No. Does it connect A and B? Very nice. Make sure it never goes down. Very nice. Very nice. Okay, Luke, yours is going down in multiple places. See what I'm talking about? Right there and to the left. Right there. It can't go down. Very nice. Although it looks like you went down right at the end.
I went a little bit above that.
Yep. Yeah. It definitely can never go above 1619, right? It can't go above and come back to B. It has to be on its way up when it hits B.
I never get this.
So this doesn't work like this.
The only, I think you're okay. I think you're okay. If you didn't get a great graph, that's fine. You can always redo it. Erase it and redo it. Okay. You can either do this on your screen or you can just follow along with me. Do you guys agree that if you took like a, let me find a ruler here. maybe. If you took a ruler and if you put it on our original line, do you agree that that original line has the same slope all the time? It's always 25.74, right? But what happens if I put it on the one that I hand drew? Do you see how sometimes it's less than that? Sometimes it's more than that? You see how it kind of rides the wave like a surfboard? You know what I'm talking about there? So sometimes I'm going more than 25 miles per hour, sometimes I'm going less than 25 miles per hour. What we're interested in, and in section 3.3, they're going to talk about calculating average rate of change. The average over a certain time interval. Well, we've already calculated the average from 0 to today, because my car did it for me. It spit out that number on my dashboard that said 25.74. But what happens if we were interested in, from 6 hours to 12 hours? What happened there? What about from 17 hours to 41 hours? What happened there? Do you see how you can take a different snapshot of a different time frame and you could calculate the average over that time frame? So here's what I'd like you to try. Get your new point tool and click somewhere on your pen marker. You got to get it right on there. And you have it on there if you can grab your arrow and you can drag it and it stays on the wave. See how my point is staying on my wave? That new point that I made, point C, stays on the wave as I drag it. And then put a second point on the wave as well. Doesn't matter where you put it. Anywhere on the wave is fine. And that one should also stay on the wave if you drag it. So now I have points C and D, which are both locked into the wave. You guys got it? I want you to connect those 2 points with a line. So I'm going to connect C and D with a line. Again, in your algebra window, I'm going to right-click on it and I'm going to change it to MX plus B form. And if you want, you can even go to the measurement tool. If you look at my screen right now, I can measure different things. Notice one of them is called slope. I'm going to measure the slope of that new line that I just created, even though it's going to spit it out over here in your equation. So you could just look at the equation if you want. But I'm going to measure the slope of that line, the one that, not my original, the one that connects C and D. And now I can move those 2 points wherever I want, and it's going to make a line, and that line will represent the average, the slope of that line, will represent the average speed from whatever 2 times that I chose to put my dots on, right? So, if I look at mine, if I drag point C to right here, and I drag point D to like right here, what do you think was happening mostly during that time frame? For me, it's roughly from 18 hours to 26 hours. This isn't necessarily realistic. What's going on right there? What does that graph indicate about my driving habits for 18 hours to 26 hours? It's almost flat, right? If the graph is flat, what's my car doing? Engine is running and it's sitting. It's not moving at all. Flat would be a slope of 0. This slope is barely bigger than 0. It's only 2.5. So really, my graph, it's not realistic, right? This is basically saying that from 18 hours to 26 hours, that's an 8-hour span, I was driving 2.5 miles per hour. My graph will probably have many more little ups and downs, not downs. It'll have many more different slopes than this. I only varied it a little bit. But this is over 63 hours. So obviously my change in speed is going to change like millions of times over 63 hours, right? So if that's a flat spot means basically your car is running, but you're not going anywhere. Now go to your graph and try to find one of the steepest intervals. When I look at mine, this interval right here ending at about 31 or 30 hours and starting at about, 20, 26. That is one of the steepest intervals on my graph. What does the slope indicate there? How fast was I going? I averaged 77 miles per hour. So what might that be? That might be setting the cruise between Valley City and Fargo, even though it covered how many hours? It covered 26.3, covered about 6 hours. So it'd be more like setting the cruise from Bismarck to Minneapolis or something like that, right? Does everybody get what we're looking at here? We're looking at average rate of change. So when we give something as a rate of change, whether it's meters per second or miles per hour, or you work 40 hours per week, or you make $12 per hour, anything that is something per something, that's a rate of change. And rates of change are always measured with straight lines and slopes, right? Straight lines and slopes. So just as a little precursor, I know several of you are Fish and Wildlife, right? Raise your hands. Fish and Wildlife students, you guys are required to take Calc 1. I guarantee you, in one of your introductory weeks in Calc 1, you're going to learn what a derivative is. Anybody take high school Calc? Anybody? So if you took high school Calc, you already know what I'm talking about. You're going to learn what a derivative is, and what's going to happen is, I created 2 points on my graph, right? C and D, and I can put those 2 points wherever I want over some time interval. Well, what ends up happening in calculus is you put those 2 points so darn close to each other that they're almost on top of each other. And that's what we call an instantaneous rate of change. Instantaneous. So I could put, C and D really darn close to each other. And the closer those two get, do you see how it almost makes like a surfboard on the wave? It's like the time gap is like from there to there. It's almost instantaneous. So that would be the speed that I'm driving at that exact second, if that makes sense. That's a calculus precursor for those of you that are going to take calc. Okay, here's what I'd like you to do. On Blackboard, I'd like you to go to Course Docs and Links. There is an activity underneath 3.3 under Day 2 called Average Rate of Change. Go ahead and click on that. It's a Desmos. And you're basically going to be doing an exercise very much related to what we just got done doing. So go ahead and work through it. And I will monitor your progress here. It's called the average rate of change of a function. The first 2 screens, you're more or less just watching stuff. And then you actually enter an answer, I think, on screen number 3. So just play around with 1 and 2. Play around with the graph and read the information. Oh, you enter your answer on slide 4, on step 4. Use a calculator if you want. And you can actually calculate it out. So for the person that typed this in, pull out your calculator and you can actually calculate it out and get a final answer. So this is no different than my car miles divided by time. Except this time you're just doing horizontal distance of a ball divided by time. Step 5 is the same. It just gives you a different problem to work on. Flag me down if you're stumped.
There's a question right here. It's asking if it represents the slope, right?
Yeah. So what? So basically, they're saying if you know anything about physics, if you don't worry about it.
Okay.
Does anybody know? Did you read the part where it says if you know anything about physics, what force is causing our ball to come down? You wouldn't even have to have taken a physics course. It's gravity, right? Yeah, you throw the ball in the air, it has some thrust, some energy that's making it go up, but eventually gravity is going to take over and it's going to pull it back down to the earth, right? That's why typically whenever you have a projectile, like you throw a ball or you shoot something out of a barrel or something like that, they typically always have that parabola or quadratic curve. And the reason they have a quadratic curve is because gravity is a quadratic function. Who's raising their hand over here? No? Okay.
So we'll just for now. Yep. Okay.
Just a little reminder from a long time ago, we said there were 4 ways that we could define a function or specify a function, and I wrote them on the board up there. This activity is not giving you any verbal description ones, but they are giving you the other 3, right? A couple of them, they gave you the graph of the ball, and you had to determine the average rate of change from the graph. On step number 11, for those of you that are already there, it involves a table of values, no graph, no equation, just a table. And then when you get towards the end, on number 12 or 13, number 12, they give you an equation, which is our 4th way of expressing a function. Now, what we did not encounter in the car problem, we did not encounter any negative slopes, because at no point was my odometer going backwards in time. So everything was positive in the car example. However, on here, you can see that you're getting positive and negatives. Like if you throw a ball and you're measuring its height, sometimes the height is moving up, and sometimes the height is moving down. For the checkbook example, this poor guy's checkbook is only going down. It doesn't go back up. That's on step 7. Double check your math on step 4. Let's see how you did that. How did you get that number? I think you made a mistake. Try it again and see what you get.
Is this when you would plug a function into each, figure out what you get, and then subtract them?
Yeah, so how did you get the 21? Or what is the 21?
2 times 2 is 4, plus 3 is 7.
Yep.
And then 5 times 5 is 25, plus 23 is 28, so 28 minus 7 is...
So you traveled a vertical distance of 21. How far did you move this way? Right? So here's what you found out. You found out the graph looks like this.
So you traveled 3.
Correct. You started here at a height of, what did you say, 7?
Mm-hmm.
And then you finished at a height of 28. So you know that from 7 to 28 is a distance of 21.
Okay.
Now, when you were here, what was your x value? 2, right? And when you were here, it was...
So you would just take the...
5.
And you would find the slope.
Correct. So rise 21, run 3, because you went from 2 to 5. So 21 to 3. So your rise is 21, your run is 3. So what's your average? 7. So if you were to connect these guys with a straight line, if you connected them with a straight line, that slope of that line would be 7.
And there wouldn't be units, right? Because it doesn't tell you.
Yeah, there's no units on this particular one.
It doesn't say that
It doesn't label the axes, so there are no units. Yep.
Since this is a rate, do we still do it the same? Or if I
So
really kinda calculate?
they're asking you the rate of change of the rate of change, right? So let me read this again. The pool at the local YMCA needs to be emptied. The table on the left shows how fast water is being pumped out at certain times. Find the average rate of change. Yeah, that is confusing, isn't it?
So you just do it the same way with the...
Yep.
Okay.
Yep. So, yeah. So, yep. They're saying what is the... It's a rate of a rate, right? Yeah. Did you guys catch that one with the swimming pool? It said it gave you the rate of gallons. What is it? Gallons per minute or gallons per hour? And then they said, what is the average rate of change of the gallons per hour, which is a rate of change? So they're saying, what is the rate of change of the rate of change, which gets a little cumbersome, right? But you can do it the same way. We still got 3 minutes left, and it looks like most of you are pretty darn close to being done. So one of your assignments will be to finish that Desmos activity. That's actually your only assignment. And then you should be caught up now with your OpenStax quizzes. We're done with 3.3. So 3.1, 3.2, and 3.3, you should be working on those quizzes. And then any practice homework that you decide to do. I want to just show you one graph with our last 3 minutes here. I just put together some random graph here. Okay? I'm going to show you what I'm talking about when I say the whole surfboard thing. When I was making that calculus reference. This is what it ends up looking like. Is that I can ride this surfboard. Oops. I can ride this surfboard, and notice my slope is right here, 36.43, or I could put it right on the line too. 36.43. Anywhere I drag this point, now I'm dragging 1 point instead of 2, because it's like those 2 points being on top of each other. Notice how as my surfboard changes, sometimes my surfboard is steep, like that's got a slope of like 68. Sometimes my slope is not very steep. Sometimes my slope is 0. I can get it really darn close to 0 here. Like that. See how that's a slope of 0? And so when we change from a positive to 0 to a negative, now I'm going negative. Now I'm on the way down. So what they call that, and this is just very common sense, they call that a local maximum. It's like the top of the hill. It's the highest point within that area. So sometimes we're on the way up. Sometimes we reach the top of the hill. Sometimes we're on the way down. When you're on the way down, notice my slope is negative, 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 negative. Eventually we're going to get back to 0 again. And that would be called a local minimum, because it's the lowest point within that area. Okay? And then we're on our way back up again. And then this particular graph just goes up and up forever. And then over here it goes down and down forever. So if you should be able to look at a graph, you should be able to identify when is the graph going up, when is the graph going down, and it's as simple as using your eyeballs, right? Positive slope, negative slope. When does it reach the top or a local max? When does it reach the bottom or a local min? And then if I gave you any 2 points, say from here to here, you should always be able to calculate those 2 points. Imagine a line going through those 2 points, and you can tell me what the average rate of change was over that time interval. So practice some of your 3.3 homework. You'll see it show up at the end of this Desmos, and then also on your 3.3 quiz. Okay, have a good one. See you Friday.